Section 5.5, Dynamical Systems and Markov Chains. A dynamical system is a finite set of variables whose values change with time. The value of a variable at a point in time is called the state of the variable at that time, and the vector formed from these states is called the state vector of the dynamical system at that time. For our first example, suppose that two competing television channels, Channel 1 and Channel 2, each have 50% of the viewer market at some initial point in time. Assume that over each 1 year period, Channel 1 captures 10% of Channel 2's share, and Channel 2 captures 20% of Channel 1's share. What is each channel's market share after 1 year? So how about we represent some variables? Let's call our first one x1 at time t, and that'll be equal to the fraction of the market held by Channel 1 at time t. And then we can make x2 of t equal to the fraction of the market held by Channel 2 at time t. How about we write x of t as a vector in matrix notation composed of x1 of t and x2 of t. Then x0 is the vector at time 0. So initially we have x1 of 0 and x2 of 0. And we were told that each have 50% of the viewer market at some initial point in time, so we'll set each one of these to 50%, or 0.5. Then we would like to figure out how this changes after 1 year. So let's look at x1 of 1, and we see that Channel 1 captures 10% of Channel 2's share, and Channel 2 captures 20% of Channel 1's share. So that means that x1 of 1 will be 80% of its own share. So I'll take 0.8 times its original 0.5. That's how much it started with, and it'll retain 80% because it's losing 20% to Channel 2. Then it'll also gain 10% of Channel 2's share, so plus 0.1 for 10% of Channel 2's, which was also 0.5 because Channel 2 started at 0.5. So working that out, we get 0.45 for Channel 1 after 1 year. For Channel 2, that'll be x2 of 1. And they're capturing 20% of Channel 1's share, so it'll be 0.2 times the original 0.5 for Channel 1. And then as far as the Channel 2 share, it retains 90% because Channel 1 only captures 10% of it. So that'll be 0.9 times the Channel 2 share, which was originally 0.5. So it ends up being 0.55. So our vector after 1 year is x of 1, and that's x1 of 1, x2 of 1, and that'll be 0.45, 0.55. For another example, how about we track the market shares of channels 1 and 2 in example 1 over a 5-year period? So how about we write, in general, x1 of, say, k plus 1. That'll be equal to 0.8 as we saw in example 1. We start with 0.8 times whatever the previous market share was. So that would be times x1k, because x1k plus 1 is the market share after the next year. It'll be 0.8 times the previous year for 1 plus 0.1, I'll use parentheses for that too, 0.1 times x2 of k, the previous channel 2 share, right? Because that's exactly what we did. We started with x0 over here and x0 over here. It was x1 of 0, the initial market share for channel 1, and over here was the initial market share for channel 2, x2 of 0. And then we got x1 of 1. So that'll be x1 of k plus 1. Similarly, we can figure out a formula for x2 of k plus 1. And that's just 0.2 times x1 of k, the previous channel 1 share, plus 0.9 times x2 of k. So then putting that together in matrix form, we have x1, k plus 1, x2, k plus 1 is equal to the coefficient matrix 0.8, 0.1, 0.2, 0.9 times the vector x1 of k, x2 of k. Okay, so now that we have our formula, let's compute x1 after 1 year. I mean, we already did it, but we can now do it using our matrix. So 0.9, and we'll multiply that by x0. So that's 0.8, 0.1, 0.2, 0.9 times 0.5, 0.5, because that was our initial state. And it, as we saw before, is 0.45, 0.55. So our formula is consistent. But now we can get x2. And that'll be the same coefficient matrix every time. 0.8, 0.1, 0.2, 0.9. And we'll multiply that by x1. And in this case, it's 0.8, 0.1, 0.2, 0.9 times 0.45, 0.55. We just plug in x1. Multiplying that out, we get 0.415, 0.585. Okay, let's keep going and get x3 now. So same coefficient matrix, 0.8, 0.1, 0.2, 0.9. This time times x2. So that's 0.8, 0.1, 0.2, 0.9 times 0.415, 0.585 this time for x2. Okay, so multiplying that out, we get x3 as 0.3905, 0.69, or 6095. Okay, 2 left, we just gonna get x4 and x5. So for x4, again, same coefficient matrix, 0.8, 0.1, 0.2, 0.9 times x3 this time. So it's 0.8, 0.1, 0.2, 0.9 times 0.3905, 0.6095. And we get 0.3 .62665. And last one for x5, that'll be 5 years after. We have 0.8, 0.1, 0.2, 0.9 times x4. So it's 0.8, 0.1, 0.2, 0.9 times 0.37335, 0.62665, and we get 0.3134. Oh, sorry, I forgot a 6.36135 and 0.638655. In many dynamical systems, the states of the variables are not known with certainty, but can be expressed as probabilities. Such dynamical systems are called stochastic processes. Stated informally, the probability that an experiment or observation will have a certain outcome is the fraction of time that the outcome would occur if the experiment could be repeated indefinitely under constant conditions. The greater the number of actual repetitions, the more accurately the probability describes the fraction of time that the outcome occurs. For example, let's interpret the entries in the state vector in example 1 as probabilities. So we had x1 equal to x1 at 1 and x2 at 1, and that was equal to 0.45, 0.55. So what we could do is interpret this as an individual picked at random from the market being a channel 1 viewer with probability 0.45 and being a channel 2 viewer with probability 0.55. So an individual picked at random from the market will be a channel 1 viewer with probability 0.45 and a channel 2 viewer with probability 0.55. A square matrix, each of whose columns is a probability vector, is called a stochastic matrix. A Markov chain is a dynamical system whose state vectors, at a succession of equally spaced times, are probability vectors, and for which the state vectors at successive times are related by an equation of the form xk plus 1 equals p times xk, in which p is a stochastic matrix and Pij is the probability that the system will be in state I at time t equals k plus 1 if it is in state j at time t equals k. The matrix P is called the transition matrix for the system. So as we saw previously, the matrix we're multiplying by was this one right over here, and this was our time xk, and then this was our time xk plus 1. Suppose that a tagged lion can migrate over 3 adjacent game reserves in search of food. Reserve 1, Reserve 2, and Reserve 3. Based on data about the food resources, researchers conclude that the monthly migration pattern of the lion can be modeled by a Markov chain with transition matrix P. So we have this matrix P, 0.5, 0.4, 0.6, etc. We have the reserve at time t equals k for the columns, and the reserve at time t equals k plus 1 for the rows. So if I was to example look at P21, then I look at the second row, first column. So that's the probability the lion moves from reserve 1 to reserve 2. It goes from column 1 to row 2. So the probability would be 0.2, the lion moves over there, and so on. So assuming that t is in months and the lion is released in reserve 2 at time t equals 0, let's track its probable locations over a 6-month period and find the reserve in which it is most likely to be at the end of that period. So how about we start writing xk? So that's x1 at k, x2 of k, x3 of k for the 3 different reserves. Okay, so x0 will be 0 for reserve 1 because it's in reserve 2, so probability 1, it's reserve 2, 100% chance it's in there, and 0 probability that it's in reserve 3. So then x1 is equal to p times x0. So I'll take my matrix P that I was given over here and multiply it by this x0 vector. So that's 0.5, 0.4, 0.6, 0.2, 0.2, 0.3, 0.3, 0.4, 0.1 times 0, 1, 0. And that equals 0.400, 0.200, 0.400. Okay, how about we now get x2? So x2 is that same matrix P times x1 this time. And if you actually take the matrix and multiply it by this for x1, then you should get 0.520, 0.240, 0.240. Let's get x3 now. So that's the matrix P times x2. And if you do the multiplication, you should get 0.50, 0.224, 0.276. Let's get x4. So that's P times x3, which is approximately 0.505, 0.228, 0.267, and how about x5? So that's P times x4, which is approximately 0.504, 0.227, 0.269. Okay, how about we finish up with x6? So x6 is equal to P times x5, and that's about 0.504, 0.227, 0.269. So notice it's unchanged from x6. In any case, we could say that the lion is most likely in reserve 1 after 6 months, because that's the highest probability. 0.504 eclipses the other two probabilities. In a Markov chain with an initial state of x0, the successive state vectors are x1 equals px0, x2 equals px1, and so on. So for brevity, it is common to denote xk by x sub k, which allows us to write the successive state vectors more briefly as x1 equals px0, x2 is px1, and so on. Alternatively, these state vectors can be expressed in terms of the initial state vector x0, because remember, x1 can be written in terms of x0. So we could substitute x1, replace it with px0, so you get p times px0, which is just p squared x0. Similarly, you could do that for x3, you get p times p squared, you get p cubed x0, and so on. So you could write every single one of the state vectors in terms of just x0 and some power of the transition matrix. So xk is just p to the k x0. So how about we use this to find the state vector x3 in example 2. So we had x0 is the same thing as x0, right? Just shorthand. So that's just 0.5, 0.5. Our transition matrix P is 0.8, 0.1, 0.2, 0.9, and x3 is equal to x3, just the same thing, just bullying you with this notation, p cubed x0, and that's 0.5, 62, 0.219, 0.438, 0.781 for p cubed. We'll multiply that by 0.5, 0.5, and we get 0.3905, 0.6095, as we did before. The matrix P, 0, 1, 1, 0 is stochastic and hence can be regarded as the transition matrix for a Markov chain. Let's find the successive states in the Markov chain with initial vector x0. So how about we compute p squared? Because every single one will just be some power of p, right? So that's 0, 1, 1, 0 times 0, 1, 1, 0, and that'll be 1, 0, 0, 1. But that's just the identity. So that means that the identity is p squared. It means that I would multiply by p again, or I could do p squared times p squared is p to the 4th. It'll also be the identity. Multiplied by another p squared, p to the 6th will also be the identity, and so on. That means that p, if I multiply by p squared, I'm just multiplying by the identity, so p cubed must be equal to p. If I multiply by another p squared, it must still be equal to p, so because the identity, so p fifth is equal to p to the 7th is equal to p, and so on. So we figured out every single power of p. It's either p or it's the identity, depending on if it's even or odd. So that means that we have x0, and then the next state would be x1, which is p times x0. The next state is p squared times x0, but p squared is the identity. So the identity times x0 is just x0. Then the next state is p times x0 again, and then x0 again, and so on. So this Markov chain only really stabilizes when x0 is equal to half-half. What I mean by that is, if you take a look at the previous examples, as we've taken more and more of the state vectors, the successive state vectors, x1, x2, x3, and so on, they seem to approach some specific value. They seem to kind of stabilize, like in the other example we had where x5 was the same as x6. Whereas in this case, the x1, x2, x3, and so on, they'll be wildly different from each other unless the starting vector is half-a-half. So I'll write that. Only stabilizes when x0 is half-half. And you can try that out. Take x0, start multiplying it. You could see that they all end up becoming half-half. We say that a sequence of vectors x1, x2 through xk approaches a limit q, or that it converges to q, if all entries in xk can be made as close as we like to the corresponding entries in the vector q by taking k to be sufficiently large. We denote this by writing xk tends to q as k tends to infinity. So similarly, we say that a sequence of matrices p1 through pk converges to a matrix q, written pk tends to q as k tends to infinity, if each entry of pk can be made as close as we like to the corresponding entry of q by taking k to be sufficiently large. A stochastic matrix P is said to be regular if P or some positive power of P has all positive entries, and a Markov chain whose transition matrix is regular is said to be a regular Markov chain. So let's take a look at an example. Let's see which transition matrices that we've looked at are regular. So we have, from example 2, the matrix P equals 0.8, 0.2, 0.1, 0.9. And P has all positive entries, so P is regular. For example 2, let's look at example 4. We had P equals 0.5, 0.4, 0.6, 0.2, 0.2, 0.3, 0.3, 0.4, 0.1. So for example 4 is also regular. So both of these are our regular ones. For example 6, we have the matrix P equals 0, 1, 1, 0. And as we saw, any power would either be P or the identity, so it always has zeros in it, so not all of the entries are positive. So this is not regular. It doesn't necessarily have to have all positive entries in P, though, by definition. For example, if we were to look at the matrix P equals 0.5, 1, 0.5, 0, then if we square that, we get that P squared is equal to 0.75, 0.5, 0.25, 0.5, and everything there is positive. So in this case, even though P did not have all positive entries because P squared does, P is still considered regular. If P is the transition matrix for a regular Markov chain, then there is a unique probability vector Q with positive entries such that PQ equals Q, and for any initial probability vector x0, the sequence of state vectors x0, px0, and so on converges to Q. the sequence p squared, p cubed, and so on converges to the matrix Q. Each of these column vectors is Q. The vector Q in this theorem is called the steady state vector of the Markov chain. So let's see if we can do some examples and find them. In example 2, it kind of became clear what we were moving towards, but let's go and see if we can actually figure out what it is. Well, again, write that P is equal to 0.8, 0.1, 0.2, 0.9. Remember that the steady state vector Q is the vector such that PQ is equal to Q. So it's essentially an eigenvector with eigenvalue lambda equals 1. So what we really need to do is solve the equation I minus PQ equals 0. Right, you could imagine moving this to the other side and factoring out Q. So what we'll do is we'll write I minus P times Q. So I minus P is 0.2 minus 0.1 minus 0.2, 0.1 times Q is Q1, Q2, and we'll set that equal to the 0 vector, 0, 0. So then by reducing this and adjoining the 0 column to it, we can get that the top row will multiply by 5. We'll see that it's 1 minus 0.5, 0, and the bottom row we could just multiply by 0, 0 out, or just add the top row to it, it's a multiple. In any case, we get 0, 0, 0. So that gives us a top equation of Q1 minus 0.5 Q2 equals 0. So Q2 is free variable. I'll set it equal to some parameter. I'll say S. So Q1 is equal to 0.5 Q2, so it's 0.5 S. And Q2 is S. So then Q is equal to Q1, Q2 is equal to 0.5 S, S, which is, I'll just write it as half S. And then I'll write that, well, these guys have to add up to 1, right? If it's going to be probabilities. So 1 has to be equal to Q1 plus Q2. So half S plus S is 3 over 2S. So solving for S, 1 is equal to 3 over 2S. That means that S is equal to 2/3. Great, so that means that Q is equal to 1/3, 2/3. Because it's half of 2/3 is 1/3, and then it's just 2/3. And that does add up to 1, and that is consistent with what we saw in example 2. It was approaching this vector. How about we also find the steady state vector of the Markov chain in example 4? So again, we'll write out P. So from example 4, that was 0.5, 0.4, 0.6, 0.2, 0.2, 0.3, 0.3, 0.4, 0.1. We'll again solve I minus P times Q equals 0. So I minus P, I'll write it as fractions. That's half minus 2/5 minus 3/5 minus 1/5, 4/5 minus 3/10 minus 3/10 minus 2/5 and 9/10. And we'll multiply that by the steady state vector Q1, Q2, Q3. Because there's 3 rows this time. Okay, so that'll equal 0, 0, 0. Let's try to reduce this. I'll eliminate the fractions by multiplying everything out so that I lose them. How about I multiply everything by 10, and I'll divide the top row by 5 in order to get to 1, or you just think of multiplying the top row by 2. In any case, I'll get that the top row is 1 minus 4/5 minus 6/5, 0. The second row after multiplying by 10 is minus 2, 8, minus 3, 0. And then the last row after multiplying by 10 is minus 3, minus 4, 9, 0. Okay, so that'll become 1 minus 4/5 minus 6/5, 0. I can get a 0 in the other rows by just adding 2 times that and 3 times that, so I'll get 0, 32/5 minus 27/5, 0, 0 minus 32/5, 27/5, 0. And I'll keep going. I'll try to get a 1 over here by multiplying by 5/32, or dividing by 32/5, whatever you want to figure, and then I'll add suitable multiples to these 2 rows to get zeros above and below. So I'll end up with 1, 0, minus 15/8, 0, 0, 1, minus 27/32, 0, and 0 for my last row. Okay, so it looks like Q3 is a free variable, so I'll write everything in terms of Q3 in terms of some parameter. Let's say S again. So Q2 will be 27 over 32S, and Q1 will be 15 over 8S, because Q1 is 15 over 8 Q3 by the first row. So Q2 is 27 over 32S, and Q3 is just S. Again, we'll take advantage of the fact that we're looking at probabilities here, so Q1 plus Q2 plus Q3 has to add up to 1, and if we add them all together, we get 119 over 32 times S. So that tells us that by taking 1 divided by that means that S has to be 32 over 119. So we get that Q is equal to 60 over 119, because that's 15 over 8 times 32 over 119, then 27 over 119 for Q2, and then 32 over 119 for Q3. And that is approximately 0.5042, 0.2269, 0.2689.